Yeah, so you all saw me like a couple of hours ago give a talk. So here I am again. And so in the second lecture, I'm going to leave behind Mond. I will not talk about Mond anymore. I'm done, I promise. And I'm going to talk about the epistemology of dark matter experiments. And so just to remind you, right, the goal of this talk is to look at, the different ways in which scientists look for empirical signatures of dark matter. They do look for empirical signatures despite the protest. Once again, protest in my talk all the time. So they do look for empirical signatures of dark matter. And I sort of want to delve into a little bit the different epistemological underpinnings for different kinds of searches and such. So that's what I'll talk about today, or in this talk. Here's the overview. I plan to, and this overview is in, So here's the overview. I'll plan to start with distinguishing between two different kinds of dark matter concepts. This is sort of part of ongoing work, sort of distinguishing between these two. Then I'll focus on searches for one of those two called fundamental dark matter. And I'll sort of describe how these experiments are usually justified. And that will also lead me to talk a little bit about robustness reasoning at the end. And then I'll conclude again. And as usual, by the way, feel free to interrupt me if you have questions or comments or things like that. Feel free to raise your hand and stuff. Yeah. So, okay. So here's the funnel again, right? I said the diagram was going to be on here as well. So you've already know dark matter plays a huge important role in cosmology and astrophysics, currently responsible for about 27% of the energy density of the universe. But it's not just in astrophysics and cosmology that dark matter takes central stage, right? It's also the case that it takes central stage in current particle physics. Here's the 2020 update of the European strategy for particle physics. So what is this document? This document is basically a consensus document generated through an open call and subsequent discussion. And finally, it's adopted by the CERN Council, and it's supposed to inform European decision makers on the future of particle physics, what research to prioritize, what experiments to fund, and so on and so forth. For people who are familiar with the North American or with the US sort of context, this is like the European equivalent of SNOMAS, basically, as far as I understand it. The European strategy for particle physics was first developed in 2006 when there was a strong emphasis on the LHC and on finding the Higgs, obviously. But now that the end of the LHC is coming closer and closer, the 2020 update is a lot more focused on what can come after the LHC. Unsurprisingly, the update's two high priority initiatives are focused on the creation of like a new Higgs factory. But when we look at the four other essential scientific activities for particle physics, the quest for dark matter is sort of identified as one of the prime motivations, right? And in fact, they say that they recommend that there are many options to address such physics topics, such as the search for dark matter or the quest for dark matter. They list a few. And the strategy recommendation is to support experiments in such diverse areas that offer potential high impact particle physics programs. And so the authors of the update recognize that the potential ways to make progress on dark matter and some other things that they identify requires a broad range of experiments, right? And this raises the question, well, what is this range of experiments in the first place, right? What are the things that scientists should pursue in the search for dark matter? And can we give sort of a systematic analysis of the epistemology of these experiments? And so what I want to do today is sort of try to start at giving such a systematic analysis of this epistemology. Quick highlight or quick sort of caveat, or not caveat, note, I guess. When I say experiment in the context of this talk, I mean experiment broadly construed. And I use this term very broadly, analogously to how cosmologists and astrophysicists tend to use it. right? That means that it's much broader than just traditional laboratory experiments. It also means huge detector facilities, but even telescopes could be like, and telescope observations could be referred to as experiments for the purpose of this talk, right? And so again, my goal is to sort of give a first step at a systematic analysis by identifying, and the way I'm going to do this, giving the systematic analysis of dark matter searches, is identifying two different dark matter concepts that I think are already present in the literature. And then I'm going to sort of discuss one example of an experiment that's particularly geared to looking for one of those two, and the other at looking, and then discuss some that's looking at the other of the two. Okay. So, as I said before, like here's how I will proceed. So let me now start with sort of identifying the two different dark matter concepts. So here's what the particle data group has to say in their opening paragraph about dark matter, right? They say modern cosmological models invariably include an electromagnetically close to neutral non-baryonic matter species with negligible velocity from the standpoint of structure formation, generically referred to as cold dark matter. For the benchmark lambda CDM cosmology adopted in the cosmological parameters, the dark matter accounts for 26.4% of the critical density in the universe, or 84.4% of the total matter density. So the fact that dark matter plays a central role in context of cosmology and astrophysics doesn't imply that all the work is done in cosmology and astrophysics, right? Some of the open questions in cosmology and astrophysics are about how dark matter behaves on galactic scales. That's part of why there's this whole thing with MON sometimes going on. And while it's generally accepted that galaxies are surrounded by a dark matter halo, what the precise gravitational potential of that halo is, what the substructure of that halo looks like, those are still ongoing questions or ongoing research projects in astrophysics today, right? And indeed, this is like part of what defenders of MOND point at when they're criticizing dark matter. They're like, well, how does it behave on galaxy scales? We don't really know that, and things like that. And so there are these open questions in cosmology and astrophysics for the behavior of dark matter. And of course, despite the central role in cosmology and astrophysics, the fundamental nature of dark matter remains severely under constraint. Right? This is why it's in the European strategy for particle physics in the first place, right? Because we don't know yet what it is, and it could be a new particle. And so, right, that's why the particle, the paragraph of the particle data group continues. They say the fundamental makeup of the large majority of the dark matter is as of yet unknown, right? And so again, when they say unknown, they mean there's this very broad range of possibilities. I know Niels showed you the cartoon from XKCD, I think, with like the mass ranges, right? And I mentioned it before as well. And so, you know, it's very much under constraint still. We have a huge mass range. I mean, there's this quip from Mike Turner, I think that it's originally from, who's like, the mass range for dark matter is a good measure for our ignorance. And given that it's like 95 orders of magnitude, that's pretty bad, right? And so this is like the particle data group also recognizes this. Now, this opening paragraph actually already reveals the two dark matter concepts that I sort of have in mind. Namely, there's the dark matter concept that functions in astrophysics and cosmology on the one hand, and there's a dark matter concept that underpins the searches for a fundamental candidate, right? And for short, I'll call these two astrophysical dark matter and fundamental dark matter. And so a first rough introduction to the distinction is the following. And by the way, this is like things that I'm working on right now, so feel free to jump in or give comments or anything. So astrophysical dark matter is the dark matter concept as it functions in cosmology and astrophysics. The reason why I say astrophysical dark matter and not astrophysical and cosmological dark matter is just because that's too long of a phrase to say, right? There's no sort of like deeper idea behind it. And so the astrophysical dark matter is the description of dark matter as it's required for lambda CDM's predictions on cosmological scales. And as it's constrained by cosmological and astrophysical observations from the CMB, from large-scale structure formation, from baryonic acoustic oscillations, from the Bullet cluster, and so on, right? And so this is like the astrophysical dark matter. Now, as I said, this is something that I'm working on, so I'm giving like very rough descriptions, but this sort of idea is also present in the current literature, in the philosophical literature as well. So for instance, in a paper from Niels on dark matter realism, which I think you'll talk about, yes? So, sorry, spoiler alert, this is part of Niels's paper, where Niels argues against dark matter realism. He gives one specific specification of what I consider astrophysical dark matter. He calls this the thin common core concept of mainstream dark matter. That's dark matter as it functions in lambda CDM. And so the thin common core concept of mainstream dark matter characterizes it as a massive field with a contribution to the total cosmic mass energy budget of 27%, thereby being responsible for certain gravity-mediated observables related to structure formation clusters and galaxies. And then there's a mass range in case it is a particle. Note that according to this description, and also based on Francesca's talk from earlier today, it is not required at all that astrophysical dark matter is a particle, right? It could be primordial black holes, for instance, right? And so this is the thin common core. I was going to make a comment on what Niels thinks about this thin common core, but I won't say anything about it because he's giving the talk later. So anyway. So that's astrophysical dark matter. What about fundamental dark matter? Well, fundamental dark matter is any specific determination of the fundamental nature of dark matter, right? It can be a particular kind of axion-like particle. It can be WIMPs or like a class of WIMPs. It can be primordial black holes. It can be sterile neutrinos. It can be a combination of several of those. If you've read Niels's paper, it's like any maximally thick dark matter concept or a combination of several of these maximally thick dark matter concepts, right? So here's an example of a maximally thick concept of dark matter, again from Niels's paper. A single type of supersymmetric WIMP with zero hypercharge, a mass of 2.8 TeV, an annihilation cross-section into standard model vector bosons of 10 to the minus 25 units, no further self-interactions, and a cosmic density corresponding to a contribution of 27% to the total cosmic mass energy budget. And so this is sort of like the basic distinction that I have in mind when I talk about these two different kinds of dark matter concepts. And as I said, right, it's not new. It's present in the opening paragraph of the particle data group's entry on dark matter. It's something that like we see in Niels's paper on dark matter realism. It's also something that very often when you listen to a scientific talk on dark matter, physicists will sort of like refer to. They'll be like, we know dark matter exists. Here's all the evidence for why it exists, but we don't know what it is, right? And so that's sort of like behind this idea of like knowing that something exists, but not knowing what it is, I think are these two different concepts that are at play, right? And so that's like the distinction that I have in mind. And so without giving you a committed description of the two concepts, I hope that I've given you some idea about what I mean with this distinction between astrophysical and fundamental dark matter. Important here, I don't want to draw any metaphysical considerations. Was that going to be your question?
Yeah, I mean,
sure. No, it's about, yeah, so yeah, this is like a struggle with terminology in philosophy. Whenever you choose a term, there's like the reasons that people have to be skeptical. The reason why I call it fundamental is sort of like you identify the individual constituents or something that collectively are responsible for this behavior, for this like behavior on cosmological and astrophysical scales. That's, if, I mean, maybe you could cash it out in emergence, but I don't think we have to go there. But even separately from those kind of questions, I don't want to draw any metaphysical conclusions from this in terms of like, can you be a realist about astrophysical dark matter without having a fundamental dark matter candidate in mind? Like, I don't want to draw these kinds of conclusions. I have ideas about it, but I don't want to draw conclusions about it for the purpose of this talk. I also don't want to suggest that one is more scientific than the other in any way or anything like that. Ultimately, right, I do think that both of these concepts refer to dark matter. It's like sort of a package deal, but I think like methodologically speaking, they do play different roles in like setting up experiments or kinds of observations. But like when it comes to what exists in the world, it's it's just dark matter, right? That's the idea. So yeah, I take it so that these two concepts are present in the scientific and philosophical literature, and they're related. They describe dark matter, just different aspects of it. So how can we think about the relation between the two? How can we think about the relation between astrophysical and fundamental dark matter? Previously, I've described it in a similar way as Niels does, which is calling astrophysical dark matter sort of the common core concept that all fundamental dark matter candidate concepts have to share. And I think that still holds, like I don't think that's wrong, but I think there's actually a more effective way of describing this that's compatible with this, which is in terms of the space of possibilities. So I actually think that as a sort of equivalent but more useful for my purposes way of describing things is by saying that astrophysical dark matter constrains or delineates the space of possibilities for everything that could constitute dark matter. And fundamental dark matter concepts pick out a point or a region in that space of possibilities, basically, right? And so suppose different ways dark matter could be, different dark matter candidates, they make up this sort of space of possibilities for dark matter. It's a very big space. It's much broader than the WIM parameter space, which in itself is already quite big, right? So it's like a very, very large space of possibilities. The boundaries, however, there are boundaries to that space of possibilities, and these boundaries are set by the astrophysical dark matter concept. And the reason to think that these boundaries are useful is things like standard model neutrinos are not part of the space of possibilities, right? Those have been excluded as constituting cold dark matter, for instance. So that's the idea behind it. And so clearly, this kind of description, I think, is compatible with this common core idea. But the reason why I want to reframe things in this way is that I think that by clarifying the distinction in this way and the relationship between the two concepts, I think we can actually start to better understand the epistemic foundations of different kinds of dark matter searches, depending on whether they're aiming to enrich the astrophysical dark matter concept or whether they're trying to identify a fundamental dark matter concept, whether they're looking for one particular fundamental dark matter candidate. And so what I mean is we can get a better grasp on the different sort of success conditions, depending on whether an experiment is looking for one or the other. So, and my working hypothesis for the distinction between the two is the following. And these are also sort of the two claims that I want to make in the rest of this talk. So empirical searches for, when it comes to astrophysical dark matter, I think that empirical searches for astrophysical dark matter essentially have to rely on eliminative reasoning. And the idea behind this is that there's limited modes of access to identifying astrophysical dark matter in your observations. And so that's why there's sort of an essential reliance on eliminative reasoning. I'll explain what eliminative reasoning is in a second. Searchers for fundamental dark matter, however, have to explicitly complement this eliminative reasoning with robustness reasoning. And this because the space of dark matter candidates being so vast that it's, and it now being excluded that there are like multiple different fundamental dark matter candidates constituting astrophysical dark matter. And so I'll explain what robustness reasoning is. But I think this has to be complemented in the searches for fundamental dark matter. I will already flag that Antonis actually wrote an excellent paper, which has just come out on robustness reasoning in dark matter searches, raising all kinds of questions for it. And so I'll briefly mention that also in the later part of this talk. Okay, good. Let's start with astrophysical dark matter and eliminative reasoning. So I think with regards to eliminative induction or eliminative reasoning, Jesus, I think probably most of you are already a bit familiar with it, but here's the sort of basic idea behind it. The basic setup is this kind of two-step process. So suppose you're given, like there's a phenomenon that you're trying to explain, that you're interested in explaining. Given this kind of phenomenon, you can first formulate an exhaustive list of hypotheses. Of course, this can be very challenging, formulating this kind of exhaustive list, but you try to formulate an almost exhaustive list of hypotheses that can explain that phenomenon. And then the second step is you run experiments, you make observations, or you make theoretical arguments so that you can exclude hypotheses from your list based on their other empirical predictions until hopefully one remains. And then the one that you've sort of come up with is taken to be like the correct explanation or the most confirmed explanation or something for your phenomenon because no other explanation sort of remain, right? That's the idea behind an eliminative induction. The idea is very old. It arguably goes back to Newton, but very recently it has been discussed by Casey McCoy as well as Chris Meek in a back and forth on eliminative reasoning to access inflation in the early universe, so about early universe cosmology. So this is sort of like the basic notion, yeah. Now, I want to show that eliminative reasoning plays a crucial role in searches for astrophysical dark matter. And I want to illustrate this with a case study about stellar streams that surround our Milky Way. And this can also shed a little bit of light on how eliminative reasoning plays out in practice and how it gets sort of anchored in observations. So let me introduce the case. So what are stellar streams? So tidal stellar streams are objects that, as the name suggests, are long sort of strings of stars. And they originate from, for instance, a globular cluster or a dwarf galaxy that was orbiting our Milky Way, but that gets disrupted. And so like, you know, like these are dwarf galaxies that you see on this image, right? And they get then disrupted. And the resulting stellar stream then sort of like orbits the Milky Way roughly around the same path that its progenitor, the original object, used to do, right? So the object from which it's originated. Now, there's one stellar stream that has garnered quite a bit of attention in recent years, and it's called GD1. It's not like there's no stellar streams explicitly depicted on this image, but so there's like the stellar stream called GD1. And it was first identified in 2006, but with the help of the Gaia satellite and the recent data releases, a lot more data has become available about the proper motions of the stars in GD1. And interestingly, what scientists have noticed is that this stream, this stellar stream, GD1, its stellar density is not completely smooth over the entire stream. It shows some gaps. It shows some variations. Most notably, there's 2 or perhaps 3 gaps. And there's also a spur. And by a spur, I mean like you have your stream and then there's like something like sticking out, sort of, at one of the gaps. Why is this interesting? Well, if your stellar stream is just orbiting through a smooth halo, you wouldn't really expect its stellar density to show much variation. You would expect the stellar density to just be smooth, right? And so the fact that the stellar stream is not smooth, that there's like gaps in it, it suggests that it somehow got disrupted by some substructure in the halo of the Milky Way, right? So, of course, we know that there is substructure in the Milky Way halo, right? There's all of these dwarf galaxies, right? So there's obviously substructure in the Milky Way halo. But it's also possible, and maybe even expected, that there are completely dark subhalos, so that there's just like clumps of dark matter that are in the Milky Way halo, right? And so that, in turn, is interesting for better understanding sort of like what role dark matter plays in structure formation, how it functions on galaxy scales. And so it can be interesting to enrich our understanding of astrophysical dark matter. And so physicists are interested in determining what caused these underdensities in GD1, with the hope that some of the causes are encounters with dark subhalos. So the first phenomenon that the physicists are interested in is obviously stellar streams. And so with regards to stellar streams, The goal is to first get the morphology of the stellar stream right. And this is no easy task. And with that in place, and given that they have identified these gaps in the stellar stream, the next goal is to identify what caused these over and under densities in the stellar stream, right? What causes these gaps in this spur? And that's the goal of this paper from 2019 from Anna Bonaca and co-authors, called The Spur and the Gap in GD1, Dynamical Evidence for a Dark Substructure in the Milky Way Halo. And so they map out, using the Gaia data release, they map out the substructure of the structure of GD1, and they identify these two large gaps and a spur. And so they ask, what is the cause? One of the two gaps they identify with where the progenitor used to be. So it's like there's a gap there because that's where the original cluster was, or dwarf galaxy, I'm not entirely sure anymore. But that got disrupted, and that's the explanation for the one gap. What about for the other gap, right? And the spur. Let's see how they go about that. The research in the cause of the GD1 features of this like gap and spur is one of eliminative induction, I think, of the purest kind. The basic approach is really the following. They identify possible hypotheses, and then they eliminate them all until one remains, right? As I was just explaining it. So Bonaca et al. Consider three potential explanations for the GD1 substructure: non-impact scenarios, luminous objects as the GD1 perturber, and dark perturbers. What are these? Non-impact scenarios would include the fact that the progenitor of the stellar stream had some very complicated structure, that somehow it was, and that this complicated structure in the progenitor is still reflected in the stellar stream today. The problem is that based on the GD1 substructure, the only way that the like observed substructure could be generated by a progenitor would be if the GD1 progenitor had a much more complicated substructure than has been observed in any globular cluster or dwarf galaxy so far. So they leave that option out immediately because like it would just be a completely novel kind of thing that they're positing, right? So this leaves impact scenarios as possible explanation. One option is GD1 was impacted by a luminous object. There's plenty of dwarf galaxies in the Milky Way. Maybe it was one of those that perturbed GD1, right? Thanks to the recent Gaia mission, for most of these, Bonaca et al. Are actually able to locate them in phase space and integrate their orbits to determine whether or how close they ever came to the location of the gap in GD1 as GD1 was orbiting the Milky Way, right? And the possibility of collision with a luminous object is excluded because none of the detected luminous satellites would have come close enough. There's a small caveat about sort of trying to double check this by having dynamical orbit data, but that's still lacking for a lot of the dwarf galaxies candidates. But regardless, based on the Gaia data, they're able to sort of make it quite a compelling case that no luminous perturber could have caused the perturbation for that caused the GD1 gap and spur. Yeah, so that's like excluded. So finally, the authors are led to potentially sort of consider dark perturbers, a perturber that's made almost entirely out of dark matter. One option is a low luminosity perturber, so which they hope to exclude with more survey data. Another option is primordial black holes, right? But the perturber would have to be much more massive than what is expected if primordial black holes constitute dark matter. And so again, based on that, they exclude primordial black holes as the dark perturber here, right? So an encounter with a massive primordial black hole would just be extremely rare and unexpected. So that's why they exclude it. And so I'm skipping quite a lot of detail here, but the authors basically conclude for dark perturbers that within the boundaries of lambda CDM, it's broadly to be expected that GD1 would have encountered a subhalo of the appropriate mass on its journey throughout the Milky Way. And that's such a perturber, that such an encounter with such a perturber could have caused the gap with the associate spur. The way they go about this is that basically they run a ton of simulations where they model these kinds of impacts and they see whether the simulations lead to the correct sort of morphology of GD1, right? And so they look for the range of possible scenarios that lead to the observed gap and spur. And it turns out that in that range of possible scenarios, that is actually very compatible with the lambda CDM predictions. And importantly, since all of the other explanations have been excluded, and this one remains, right? They conclude that it is in fact likely that it was such a single dark perturber that caused the impact on GD1. And so important to note here, right, is the reliance on eliminative induction in this local context is crucial. They couldn't have concluded to the dark perturber scenario without relying on eliminative induction. And it's in a sense sort of inevitable. Why? Well, if the GD1 spur and gap feature were caused by a dark subhalo, it's hard to see how that subhalo could have been identified outside of its effects on GD1 in the first place, right? There's outside of its effects on the stellar stream. So ideally, scientists would like to, and maybe follow it up with some lensing observations, but it's not always clear that you're going to be able to do the required lensing observations. And obviously, there's no electromagnetic counterpart that you can observe, right? It's the dark perturber. That's so that's obviously unavailable. And so this is why the reliance on eliminative reasoning, I think, is sort of essential in this kind of context, right? Now, if it really is the dark perturber that has caused this, oh, sorry, yes, go ahead.
Are they able to make an estimate about the density of the hypothetical dark fibers from the surrounding process?
If I remember correctly, they are able to estimate like the mass range and such. Yeah, they're able to constrain some of the properties of the subhalo. Yeah, but I'm not gonna, I don't remember numbers or anything like that. Yeah. Yeah.
Since we're both fans of Jacob's and his collaborators now take the history of dark matter, I was wondering how your account of limited reasoning fits that. But there it seems like the wiki and the clusters, it didn't seem like, oh, with a bunch of explanations, dark matter, non-equilibrium,
yeah,
modifying laws, and they cross them off one by one. No, it's 1974. So
it's just like bringing a bunch of stuff. Yeah. Yeah, so that's a good point. So I don't think that historically necessarily this is how it works. And I think, so Niels is describing sort of this history of how dark matter came to matter is as Jaco de Zwart describes it. And part of the, or like what he argues quite convincingly, I think, is that it was like scientists, like two different groups of scientists sort of almost simultaneously realizing that a bunch of different observations could have been brought together. There was also like theoretical considerations. They still wanted to close the universe at the time, things like that. And sort of all of that together leading to the acceptance of missing mass. So I don't think that that necessarily, that like my account is going to apply to those early days. And I think I can get away with that because I think that's sort of like how the hypothesis actually came to be. I think nowadays it's a much more mature sort of research field, even though there are still so many open questions. And I think this is more of a representation of how the research evolves today, actually. Yeah, but it's a fair point. But to your question about the dark matter subhalos, this is where I move to next, right? So if it is really, if the eliminative inference really holds, this means that the stellar stream observations can actually provide evidence for the existence of dark matter subhalos and can help us constrain this, right? And so this is what Bonacca et al. Conclude in their paper. This is like the closing paragraph of the paper. Further study of the GD1 gap and spur feature may provide the first opportunity to follow up an individual halo substructure. But most excitingly, these features demonstrate that cold stellar streams are extremely fine-tuned detectors, sensitive at a level that was only hoped for beforehand. In addition to GD1, there are over 40 known streams in the Milky Way halo. In the era of Gaia, this is the satellite, we now have both the incentive and the resources to study them all in detail. With a full network of streams, we could learn not only about individual halo substructures, but about the population as a whole. So what's at stake here, right, is that the authors are raising the possibility of using stellar streams to identify individual dark matter subhalos, but also to basically create a whole census of dark matter subhalos. And that kind of census gives you constraints on the population of these dark matter subhalos. So, that kind of census can give you important implications for astrophysical dark matter, right? It could give a better handle on how dark matter behaves on galaxy scales, right? And on cluster scales. So this is why this is important. But there is also an important challenge here. There's an important challenge in the narrative that I have been building. Because the identification of individual dark subhalos or constraining the subhalo as a whole depends crucially on the adequacy of this eliminative inference that I was talking about earlier, right? But setting that inference up comes with challenges, as is illustrated by this paper by another research group. These authors re-examine GD1, and there are a couple of points at which they deviate from Bonaca et al. First of all, they disagree on the stellar stream phenomenology that needs explaining. They actually don't think that the stellar stream is associated with the gap that Bonaca et al. Think. And moreover, they identify a third gap. There's an additional sort of underdensity in the stream. How is this possible? Well, identifying members of the stream is extremely hard because you have to try to sort of disentangle the stars that are members of the stellar stream from the stars that are in the Milky Way disk, right? And sort of, and you have to do that based on their particular proper motions and such, but that's an extremely challenging task. So that's why this is possible. Now, since they reconstruct the morphology of GD1 differently, perhaps unsurprisingly, the elimination of hypotheses for explaining the sort of substructure of GD1 is going to be different as well, right? These authors actually think that the spur feature could be due to an encounter with one of the luminous satellites in the Milky Way, rather than some dark substructure. So they think that, in fact, the luminous perturber scenario can't be excluded. But just to sort of, for completeness and to reassure you that cool science can still happen, they don't give up on the mission to use stellar streams to identify to sort of constrain the dark subhalo population of the Milky Way. But they use a different methodology. Instead of focusing on identifying single perturbers that are responsible for one particular underdensity, they actually try to use the overall power spectrum of density fluctuations to constrain the dark subhalo properties as a whole. So basically what they're doing is like, they're assuming that the substructure in the stellar stream might not be due to like one big perturber causing a huge effect, but it might be sort of like overlapping effects of encounters with a bunch of different subhalos that ultimately leads to the observed sort of substructure. Of course, in order to be successful in like sort of using these like overlapping encounters, these scientists still have to be successful in excluding the effects of luminous perturbers, right? So you're still faced with the fact that you're going to have to eliminate effects of luminous satellites before you can start constraining the dark matter subhalo population. But yeah. Now, there is a third target that the stellar streams are used to constrain. And that is sort of like, and now I want to go back to these two dark matter concepts I had in mind. I talked about stellar streams, I talked about dark halo substructures, but what does this teach us about these two dark matter concepts? Well, I think that the stellar stream case gives an example of how astrophysical dark matter can be further constrained, right? How the boundaries on the space of possibilities for fundamental dark matter get tightened, basically. Because remember, right? Astrophysical dark matter constrains the space of possibilities for fundamental dark matter. And so if you enrich your astrophysical dark matter concept, that amounts to tightening the boundaries on your space of possibilities, right? And in the current case, it turns out that there are fundamental dark matter candidates that would lead to sort of a different kind of substructure than what your stellar stream gives evidence for. So basically, certain kinds of dark matter candidates lead to predictions for halo substructure that's sort of incompatible for what we expect based on the kind of dark halo substructure that would cause the density perturbations in GD1, right? And so by determining the properties of the dark matter subhalo populations using stellar streams, astrophysicists are able to put tighter constraints about what fundamental dark matter concepts could be compatible with these observations, right? And so this is like the third target. And so you see this, for instance, so some of the researchers in the second stellar stream paper that I showed you wrote a separate paper, and they write in that separate paper exactly on sort of constraining the particle nature of dark matter from stellar streams. And they write the way stellar streams, and so they write basically the evidence for CDM substructure thus obtained can be used to constrain any particle dark matter that leads to a substantial suppression of the dark matter subhalo mass function on subdwarf scales. Right. So more specifically, by the way, they derive sort of stringent constraints on the mass of warm dark matter relics, basically from these stellar stream observations. So they sort of constrain things further. Okay. That's the first part of what I wanted to do today, and sort of the overview of the stellar stream case. So in this reconstruction, right, what I've tried to show is that the detection of astrophysical dark matter with stellar streams depends on eliminative inferences, and that establishing these inferences, it does come with challenges though, right? But I've also tried to show that stellar streams are used to constrain these three different targets. Sorry, targuments, that doesn't make sense. Sorry, it's after lunch, 3 different targets. So scientists are trying to map out the population of subhalos in the halo of the Milky Way. But that mapping out of subhalos to then constrain astrophysical dark matter is only possible insofar as authors can accurately map out the stellar streams, the substructures themselves, and the impact scenarios that give rise to the stellar stream substructure, right? So the exploring of the dark matter subhalo population crucially depends on the success of the stellar stream research itself. If they don't get the morphology of GD1 right, then they don't get the sort of perturbation scenarios right, then they won't get accurate constraints on this, on astrophysical dark matter, basically. And so this sort of establishes the first thing that I wanted to show, that empirical searches for astrophysical dark matter essentially rely on eliminative reasoning. Other questions at this point? Mm-hmm. Mm-hmm. Well, yeah. So the Wheat miracle. Yeah. So I don't know how. What do you mean by the Wheat miracle?
What's very confused by the Wheat miracle? So I'm not sure.
Well, what do you? So I guess I don't mean what do you mean by the Wheat miracle, but sort of like what do you mean? How would it constrain astrophysical dark matter?
Most common events think, oh well, is the Wheat miracle.
I think that's like a nice feature of a fundamental dark matter candidate. Yeah, because it's not necessary that dark matter is like, it doesn't have to be thermally generated, right? In the early universe, like it's possible that it's not, that it's otherwise generated. So I think the only way in which like your fundamental dark matter concept is going to really constrain astrophysical dark matter is like if you can like eliminate large swaths of the possibility space. It might be that in some of those cases, you can actually get sort of better constraints on astrophysical dark matter. I think the exception is if, and this is like the second part of this lecture, the exception is, right, if you find positive evidence for one of these fundamental dark matter candidates, which we haven't found yet, and you're able to like, and you're able to convincingly establish that that's the only dark matter candidate, which is a separate challenge, right? Because like, it might just be that there's multiple ones, or that there's like multiple components, that there's a whole dark sector that we don't know about. But if you're able to establish that you have found it and it is the only one, then yeah, it like all of a sudden your entire space of possibilities collapses down to that one fundamental dark matter concept. And then the two get identical, I guess, right? They sort of become the same. And that's ultimately the goal. Yeah, while you're working towards it, I don't think that like the reverse is going to be that big compared to the. Mm-hmm. 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 Yeah, that's a good question. Are there other questions? If not, I propose that we take a break now, and then we'll do like 10 minutes or so, and then I'll continue with the second part later.
The example you put on a substructure is very, very relevant. Although the analysis you have been focusing on maybe it's not
the best one.
the one that I would take as clearest.
Okay.
There's a lot of dirty physics that is going into how you model these stellar streams. And the dirtiest point is that really you don't have so to speak, self-consistent initial conditions. No, you're essentially evolving this the sub-halo and the parent halo. Not as if as we are both in the same kind of initial condition.
I see.
Merge, but sort of they are two distinct things.
Oh,
You come back in Stockholm with a lot of weights.
oh, thank you. That's amazing. Thank you. Thank you. You'll have to sign it for me. Yeah, I mean, when the honoree is here, then like I have to get a signature, obviously. I see.
So, I mean, it's like you make this exercise as if they are bodies that don't know each other and they are colliding and one. So then doing the exercise of reconstructing a statistics out of it. Once it's not a single event that has one huge imprint, it's going to be very, 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 very difficult.
You like
Thank you. Amazing. So you think like the single event imprint, if it could be a single event, like it could still hold, but that's going to be extremely rare, basically. I see. Ah, interesting.
So on the other hand, there are all these studies that look at substructure gravitational lensing.
Yeah.
Cluster in cluster. And there, say the observation is much more clean.
Right. Yeah.
Really detecting dark spots
right.
where darkness. So to speak. And then also that problem is, since it is in cluster, it's closer to the linear regime, which is the regime in which we understand. So there you can insert the initial conditions to proper way, and you can do proper waste.
I see. But I was told by someone, and so correct me if this is wrong, that like although the gravitational lensing is indeed this different route of getting at substructure, that it's not that it might be the case that sort of the that you kind of with the stellar streams you might be able to access certain mass ranges for substructure that you aren't able to access with gravitational lensing.
Yeah, gravitational lensing, so to speak, they're probing. So in this embodied simulations,
right?
Since dark matter is scale 3, pretty much what you see on a given patch that you populate somehow, you scale it down to a smaller patch, they are so similar. But then if you are imprinting some physical property that matter on a physical and scale, that's what you are going for. So they are probably slightly different things. So with stellar streams, they dream to see the cutoff in the power spectrum from the dark matter. In the cluster, they constrain more the shape of the power spectrum, and also on the shape of the power spectrum, there is some imprint from, say, if you are talking about warm dark matter, there will be some imprint even there. If you are talking about something which is more exotic, and maybe you did mention this fuzzy dark matter, then it's a different thing. In cluster, you wouldn't see anything.
I see.
So,
I see.
There it will depend on the model, whether they're sensitive or not.
I see. Okay. But so they,
But trust me, if this goes ahead and gets controversial, people will start fighting against this, because this is indeed has some underlying assumptions which are really shaky.
I see. No, that's good to know. But it's sort of, yeah, no, that's very good to know. But it's interesting. Like, in order to make this to work, they have to do a lot more theoretical.
Yeah, it's theoretical, but it's also tricky, no?
Yeah.
Because you are starting from a system whose initial condition is difficult to do.
Yeah. I see. I see. But that's good to know. Thank you. That's very useful. Thank you. We have something. Ah, there you go. This is very cool. This is great. '21. Cool.
It's like starting YouTube really fast.
Oh my gosh. Oh no. Oh, very cool. Oh, did you ever end up having the meeting? Did you ever end up having the actual meeting?
Well, not possible.
Oh, that's sad. Yeah. Not an ideal time. But still, this is great. Yeah, it's very nice. Thank you. I'm very happy with this too. Oh, let me put it away. There we go. There we go. Wait a little bit longer. Okay, should I start again? Everyone bricked out sufficiently? Okay, cool. So, good. I've started with like talking about the empirical searches for astrophysical dark matter, relying on eliminative reasoning. But what about searches for fundamental dark matter, right? That's what I want to turn to next. And as a starting point, recall Niels's cartoon, right? Well, not Niels, but Niels showing the cartoon of this like enormous mass range. So fundamental dark matter is extremely under-constrained. Nonetheless, there are lots and lots of experiments that are underway that are looking for fundamental dark matter candidates. Here's some examples. So there's the LZ experiment. There's the ADMX experiment. Here's a bunch of philosophers of science visiting the ADMX experiment in Washington, or, you know, at Atlas in CERN, one of the detectors that was used in the discovery of the Higgs, right? There's like a bunch of different experiments going on at Stockholm University. There's lots of people looking for axions, dark matter there. And so all of these experiments are taking place despite the fact that very little that is, despite the fact that fundamental dark matter is extremely under constrained. Like there's very, like the boundaries we get from astrophysical dark matter are very minimal to a certain extent. And the boundaries, like what they do tell us is that whatever fundamental dark matter is, it's not gonna be like anything that has been detected by particle physicists until now, right? It's unlike anything that is discovered so far in terrestrial physics. It's unlike anything that the LHC has led us to discover or anything like that. And so this makes a general question about sort of how science works particularly salient in context of dark matter. This is sort of an example of how I think dark matter research can like teach us new things about existing ideas in philosophy of science. Because how does science make progress in attaining knowledge about the world? That's by running experiments. But scientists don't just run any experiment that they can come up with, right? If anything, the current funding situation just doesn't allow for that, right? And in addition, there's also moral constraints and feasibility constraints that come into play. But even within the boundaries of what's like ethically permissible and practically feasible, the number of possible experiments is much, much, much larger than the number of experiments that are actually run in reality, right? And so how do scientists justify their use of a particular experimental method to investigate a given target then? In other words, right, how do scientists justify that they're choosing one type of experiment, one type of experimental methodology to investigate a particular target, and that methodology is going to be particularly effective in delivering useful data for their purpose? And so in the light of dark matter, this becomes particularly pressing. Because why is it, right? Like this is like a very naive question in a sense, but why is it that all of these funding agencies and all of these scientists think that the experiments that I was showing earlier can be useful in detecting fundamental dark matter, given that we know so little about fundamental dark matter, right? Why is it that these methodologies are supposed to be useful? And so this is the answer. This is the question that I want to focus on in the second half of the talk. And I will argue that in scientific practice, there's different ways of answering this question. And I'll argue that there's sort of like a spectrum of what this justification looks like. And I'll argue that the dark matter experiments and the way those are justified lie on one end of the spectrum, which is different from most scientific experiments that we usually think about. And this will then in turn set me up to argue for the requirement of robustness reasoning in searches for fundamental dark matter. Okay, so we'll take sort of a roundabout way towards this second claim. So very briefly, just some terminological clarification before I start. A method is any activity that generates empirical evidence where that activity can be applied in various research contexts and to various targets. So it's a very broad idea. And a target T is that system in the world about which a scientist's research aims to generate knowledge, specifically to explore and model the features and causal interactions of the target. So that's sort of like the general terminology that I'm going to use. Okay. Now, For instance, right, like to give you an example, suppose that you're interested in finding out things about the structure of the human body or the human brain maybe is your target. And then one particular method that you may use to identify sort of different structures in the human body is MRI machines, right? That's an example of a method, okay? So how is it that experiments are usually justified? And I'm again using a term that, so I've called this a target-driven logic. But this is like sort of a general structure. And I take this to be quite common. And I'll give the general structure first, and I'll then apply it to an example, right? So the general structure is, suppose you have a target system T, and it has some known features or properties A and B. You have method 1 that uses feature A of T of the target to uncover potential new feature X. You have method 2 that uses feature B of T to uncover potential new feature X. And you have method 3 that uses feature C of T to uncover potential new feature X. Now, obviously, since methods 1 and 2 use features that you know the target has, properties that your target is known to have, while method 3 uses a feature that you don't know whether your target has it, the preferred methods to uncover a potential new feature X will be methods 1 and 2, while method 3 remains out of consideration for now. You won't use that to start running an experiment for now. Why do I call this sort of a target-driven logic? The basic idea is the justification for the method choice appeals to pre-existing knowledge of your target system, right? So like the grounding sort of motivation for your method choice comes from what you already know about your target, for which you have ample experimental evidence already. So here's an example, right, applied to an example. So again, given that scientists are trying to sort of investigate different regions of the brain, for instance. So given the human body, which contains different types of soft tissue that contain protons, MRI uses strong magnetic fields that cause the protons in different tissues to align at different times. And this then can allow you, oh God, what terrible typos on here. And so this can then differentiate between different types of tissues based on this like different alignment time. Sorry, this like, I definitely did not proofread this well. I'm so sorry about that. So scientists can use these MRIs to study brain structure and other soft tissues in the human body. And they're going to use, say, MRI machines over optical microscopes, which cannot look through, say, human skin, right? Because that you can't use to sort of like examine the brain. So this is like the target-driven logic. So far, so good. I hope this is like fairly plausible to everyone, that you're just like, you know, you apply the, or like you sort of put the knowledge that you already have to good use to identify what next experiment is going to be fruitful, right? But what about these dark matter experiments, right? Because as I mentioned before, fundamental dark matter is very under-constrained, right? And so this looks pretty dire for the target-driven logic that I was just explaining. But I mean, it can't mean that scientists are completely lost when trying to set up experiments, right? Because otherwise, how come these experiments are being run? And there's many, many more examples of dark matter searches that are being run. How are these experiments then justified? I think that in these cases, there's a different kind of structure of justification at play, a different kind of logic, if you will. And I called this a method-driven logic. And let me again run through the entire structure and then apply it to some examples. So here's the entire structure. So given a target system T, right? Method 1 uses feature A of T to uncover potential new feature X. Method 2 uses feature B of T to uncover potential new feature X. Method 3 uses feature C of T to uncover potential new feature X. It started raining really badly. I don't know if it's like, once again, protest against anything that I say. But I'm going to keep going. Notice, by the way, that these first 4 premises are almost identical for the target-driven logic, except for the first one, right? We don't have a lot of pre-existing knowledge about our target, basically. And because this first premise is different, the rest has to be different as well. And so now it's no longer the case, it's no longer sort of pre-existing knowledge that our target has features A, B, or C that I was talking about before. So if T has feature A, method 1 can be used to uncover new feature X. If T has feature B, method 2 can be used to uncover new feature X. And if your target has feature C, method 3 can be used to uncover new feature X. And because we're now dealing with conditional statements, right, we have to, the next question is like, which of these antecedent clauses can we sort of plausibly believe, or can be sort of triggered in a responsible way? So we have another premise. It's either possible and plausible, hopefully, that our target has features A and B, but it's either impossible or implausible, but maybe possible, that our target T has feature C. Note, plausibility here is different from what is established through like empirical confirmation. It's more like you have sort of like heuristic reasons to believe in something. And again, I will give an example. Jishen, you have a, yeah. So they're experimental protocols. They're like types of experiments that you run. And they could be very broad. I mean, like in principle, they could be any kind of experimental protocol. Right. Well, but so depends. What is your back? So what do you? Yeah. Yes. You always need some background theory when constructing an experiment. The problem that I'm pointing at here is that in some cases, sorry, let me step back. You always need some theory. You need a theory of your detector. You need to understand how your detector works and like the different systematic errors and things like that that are associated with it. Absolutely. What I was pointing at with the target-driven logic was that you also use theory of your target to sort of say like, because of what I already know about my target, I'm going to use one method rather than another, right? In order to learn about the human brain, I can use MRIs. Optical microscopy is not going to teach me anything about fundamental MRI, about like functional like regions of the brain, because in order to use an optical microscope on a brain, the subject needs to be deceased. And so that's not going to teach me anything about functions of the brain, for instance, right? And so, so that's like a very basic sort of pre-existing knowledge of your target that's sufficient to be like, okay, MRI is a good method, optical microscopy is not. Obviously, given your pre-existing theory of your target, very often there's still going to be multiple methodologies that you might be able to use, right? Like for identifying certain medical conditions, I think, I might be wrong, but I think you can use both echoes and MRIs and X-rays or something like that, or maybe not all three, but like both of these, right? Some subset of them. In that case, there might still be sort of additional pragmatic reasons, right? Sort of, you might not want to be putting people under too much radiation or something like that. So there might still be other reasons for making a choice. But the basic idea as to why you think your method is going to be effective has already been given based on like what you already know about your target, right? Yeah. And so the problem here is we don't know much about our target. That's the issue, right? That's the idea. Good. So, right, so this is the sort of overall setup. And then the conclusion for the method-driven logic is going to be similar to the one for the target-driven logic, because that's what we're trying to do. Some methods are going to be more preferable to uncover a potential new feature X compared to other ones, right? So what's particular, again, about this method-driven logic? As I was mentioning just now, right, in response to Yushen's question, is that unlike in the target-driven logic, the justification for the method choice is not going to be primarily appealing to what we already know about our target. Rather, it's going to be primarily about what does our target need to look like in order for a given method to be effective? And can we make the case that our target could look like that? So that's why I call it sort of a method-driven logic. Because we don't actually know whether or not our target has these features or not, but we're trying to make the case that it's at least possible, right? And using the method-driven logic in a responsible manner sort of requires that these assumptions are plausible and at least possible. But it doesn't require sufficient empirical evidence to accept that the assumption is true, right? So how does this play out in dark matter context? First, you need to define a target, and that we've already done. the definition, unsurprisingly, comes from cosmology and astrophysics, right? This is the astrophysical dark matter that comes back again. This definition is fairly thin, as we already know. And particle physicists are primarily interested in features that this definition does not describe, right? They're very much interested in how it couples, how dark matter may couple to standard model particles through other interactions than the gravitational ones. And so the problem is with astrophysical dark matter, that definition doesn't even tell us that there is such a non-gravitational coupling in the first place, right? It might just be that there's no such non-gravitational coupling. But so the particle physicists are exactly interested in finding these additional features. So how do they look for them? A first kind of experiment, and I think in some later lectures from physics background, you'll probably hear more about them. First kind of experiment looking for certain type of dark matter particles are called direct detection experiments. They've been around since the 1980s, and they're like continue to be a main player in looking for dark matter particles. And they're going to be what I'm going to primarily talk about. I think you've already seen this diagram. Yes? So great. Thank you, Niels. So, right, direct detection experiments. So you read it from top to bottom for time. So the idea is that you have a dark matter particle coming in, colliding with a standard model particle, and then depositing some recoil energy, like going, continuing along its way, but depositing some recoil energy that hopefully can be in, and hopefully that can be detected, right? That's the idea with direct detection experiments. How do these direct detection experiments constitute a method-driven logic? I'm going to run through the argument, and then I'm going to give you background on each of these premises. So given astrophysical dark matter, it's our target. Neutrino detection experiments use the weak coupling of neutrinos with an extraterrestrial origin to detect their presence by the deposited energy and scattering events of neutrinos from atomic nuclei. If dark matter particles are weakly interacting, have a mass of the order of 100 GeV, and exist stably in the galactic halo, detectors similar to those used for neutrino detection can be used to search for signatures of dark matter particles existing in the halo of the Milky Way. Based on astrophysical evidence and the WIMP miracle, it's plausible that dark matter particles are weakly interacting, have a mass of the order of 100 GeV, and exist stably in the galactic halo. So detectors similar to those used for neutrino detection can be used to search for signatures of dark matter particles existing in the halo of the Milky Way. Clear? I'll go through it. So the first premise, given astrophysical dark matter, right? That's just like, again, this astrophysical dark matter concept that I've been talking about before. The second premise describes the experimental method, right? The experimental protocol. And it refers here to neutrino detection experiments. So what are these neutrino detection experiments that I'm describing here? Well, here's a picture of super Kamiokande in Japan, and the successor of the Kamiokande detector that was constructed in the 1980s. And one of its main successes was detecting solar neutrinos, right? And so how did they achieve this? Well, they have this giant vat of cleaning fluid, basically underground. And when a solar neutrino comes in, it will scatter off of one of the particles in the detector fluid. And that in turn will lead to a signal that can be hopefully, there's a lot of steps along the way. I'm simplifying a lot, but that hopefully one of these detectors that you see sort of along the side, hopefully one of those will pick up the deposited sort of the recoil energy, and that will pick up the signal. And so this is sort of, in a very simplified way, this is the method under consideration. Have giant vats of detector fluid and have detectors along the side of it that pick up when there's a particular kind of recoil, right? When there's a particular kind of scattering events. Next, there's the conditional. Right? So this is like the conditional where we're like making all of these assumptions about our target. And this is where the neutrino method basically gets repurposed to dark matter searches, but where certain assumptions need to be made to justify this kind of like repurposing of the neutrino detection method. And so, right, it's again, in the 1980s, when dark matter had already sort of been established, it was this parallel with neutrino detectors that particle physicists appeal to in their development and justification of direct detection experiments, right? Here's just one example of one of the papers from that period by Goodman and Witten in 1985. They write, dark galactic halos may be clouds of elementary particles so weakly interacting or so few and massive that they are not conspicuous. Recently, Drucker and Studolsky proposed a new way of detecting solar and reactor neutrinos. The idea is to exploit elastic neutral current scattering of nuclei by neutrinos. The principle of such a detector has already been demonstrated. In this paper, right, so they've already have the principle of this kind of like scattering detection. In this paper, we will calculate the sensitivity of the detector to various dark matter candidates. I won't go through the details of the calculation for your purposes, but they managed to calculate that it would be sensitive to it. Here's another one from 1980s. Recently, a new type of neutrino detector, which relies on the idea that even small neutrino energy losses in cold material with a small specific heat could produce measurable temperature changes, has been proposed. The purpose of this paper is to examine the possibility that such a detector can be used to observe heavy neutral fermions in the galaxy. Such particles, it has been suggested, could be a substantial component of the cosmological missing mass and would be expected to condense gravitationally, in particular, into galactic halos. And so in both cases, right, you see explicitly this parallel between neutrino detection methods and using it to find this missing mass, right, to find dark matter to detect dark matter particles, right? And the remainder, like both of these papers are then devoted to determining what kind of assumptions need to be made about dark matter. This is where mass ranges come from, as well as assumptions of the weak interaction and things like that, right? Okay, so they've made all of these assumptions, and if dark matter satisfies those assumptions, then yeah, sure, you can use something like neutrino detection techniques for finding dark matter. But do these assumptions actually hold? Are they possible? Are they plausible? For that, a lot of direct detection searches, and definitely those proposed in the 1980s, I think, appeal to the constraints from cosmology and astrophysics and to what is possible within these constraints, right? Here's a review article from 1988 on direct detection searches, and they write, superclusters are the first to form in a neutrino-dominated universe, and smaller scale structures such as galaxies can form only after the initial collapse of supercluster size fluctuations. However, the weight of the evidence suggests that galaxies are much older than superclusters, which are only now beginning to collapse. For this and other reasons, hot dark matter is generally regarded as less successful than cold dark matter. So basically, they're excluding standard model neutrinos based on the available theories of structure formation, right? And so we see that astrophysical dark matter, this fairly thin concept, it's still crucial because it's sort of like determining what are the possible assumptions that you might make about the properties of dark matter particles. But moreover, there's more to the story. It's not just possible that dark matter particles would be of the particular mass and interacting through the weak interaction, but it's even plausible that these things or that these properties are satisfied, at least for WIMPs. And that is because of the WIMP miracle, which Niels was mentioning earlier, right? And so the WIMP miracle, right, is the idea that if you use WIMPs in the early universe and you let them thermally, you let them thermalize basically in the early universe, and then you see when the annihilation and production of WIMPs freezes out when the universe expands and cools down. It turns out that the abundance of WIMPs you get is exactly the right abundance that you need for dark matter, right? And so this is the WIMP miracle. And this was sort of a good plausibility argument that dark matter would be constituted by WIMPs, right? And so the WIMP miracle makes it at least plausible that dark matter has the required properties, but it does not by any means provide conclusive evidence, of course, right? And so based on all of the previous information, we end up with this conclusion about dark matter experiments. Now, or in the words of the authors from the review article, the exciting possibility exists of detecting WIMPs in the laboratory. Okay. Hopefully you're still following me. And I've sort of convinced you about the sort of justification and that and you're sort of convinced that direct detection experiments provide a clear instantiation of this, what I've called this like method-driven logic, right? But how does this get us then to robustness? Let me make that a cliffhanger. Are there questions at this point? No? Okay, cool. How do we get to robustness? Well, I've proposed so far, right, that there's these two logics at work in justifying method choices, a target-driven logic and a method-driven logic, right? And the target-driven logic appeals to this pre-established knowledge. The method-driven logic appeals to what features the target would need to have in order for the method to be effective. And I've then argued that this method-driven logic is important in dark matter searches. But now let's return to these dark matter searches, right? So the method-driven logic lies behind the searches, but behind direct detection experiments like LZ and like ADMX, right? Those are sort of two examples. But it's also used to justify other dark matter particle searches, for instance, at CERN, right? For instance, at Atlas. Here again is our familiar Feynman diagram. And these other kinds of, they don't want to hear about production searches. These other kinds of, so the kinds of searches that happen at Atlas are production searches, right? And so for them, you read the Feynman diagram from right to left. And the idea behind production searches is, right, you collide standard model particles and then hopefully produce, right, some dark matter candidate particles, which will show up likely as missing energy. And so you then try to find those, right? I won't go into details, but I do think that these kinds of collider searches for dark matter are also justified through a method-driven logic, right? But the kinds of assumptions that are required to justify these kinds of experiments are very different, are kind of different, not very, but kind of different than the ones that you rely on for the direct detection experiments. Because in accelerator experiments, the sort of feature that you're relying on is the coupling of unknown particles to standard model particles to detect these unknown particles or couplings in the form of excess events, right? And so the assumption about dark matter are then that either it depends on the kinds of searches that they're running, but one type of search is like assuming that dark matter is constituted by some supersymmetric particles. And so then the search is explicitly for supersymmetric particles. Or there's this idea that there's a particular kind of coupling to standard model particles, for instance, something called invisible Higgs. And there, the idea then is that like there's a particular kind of like mediator or sort of gap that you're sort of looking for in these experiments, right? So these are a different kind of justification for the experiment, a different kind of search for dark matter. And at first sight, this is a very good thing, right? There's multiple ways of accessing this enormous space of possibilities that I've mentioned several times now for dark matter particles. And so such multimodal evidence in general is considered good in philosophy of science, right? There's sort of what we call multimodal evidence. This is evidence that comes from different kinds of experiment. In general, is considered often good and sometimes also necessary, right? So the idea behind multimodal evidence is that there's a collection of multiple lines of evidence where each line comes from more or less independent experiments and observations. And independence is referring to the fact that these experiments use different methods that are subject to different sources of systematic errors, right? So if you have multimodal evidence, then likely you have like lines of evidence that come from many different experiments that are subject to many different systematics. And so if they agree, the ideas, that gives you good reason to believe in your experimental result, because it's much less likely that your experiment will, that like all of your experiments will have been subject to such systematic errors that they happen to align all on the same value or on the same result. Whereas it's much more likely or a much more plausible explanation that your result is just an accurate representation of what the world is. You've actually detected something, right? And so this is why sort of in general, multimodal evidence is considered a good thing. Another term that philosophers often use when they have multimodal evidence for an empirical result is saying, indeed, robustness. They say that an empirical result is robust, right? So this gets us to, this is what I mean when I talk about robustness reasoning. And in the case of dark matter searches, there's multiple different reasons why you might need multimodal evidence, right? One reason is different kinds of dark matter searches are sensitive to different parts of dark matter parameter space. Like even if we're just talking about WIMPs, different kinds of searches are sensitive to different areas of the WIMP parameter space. And so you kind of need multiple kinds of searches so that you can exclude more of parameter space. Like you could just cover more of parameter space. You don't want to, I say exclude because that's all that has happened so far. Ideally, you'd find something positive, right? But yeah, so you can basically cover more of parameter space. So that's one reason. But there is also another reason, which is that suppose one of these searches gives you a positive result, right? Suppose that one of these method-driven experiments gives a positive signal. Can scientists immediately infer that they have, in fact, identified a dark matter particle? That's not obviously going to be the case, right? Because remember that scientists had to make a whole bunch of additional assumptions to even get the experiment off the ground in the first part, in the first case. So like in the first place. There's this sort of like, wait, we built up all of these assumptions about our target to argue that we're actually detecting dark matter. But like, given that we have a positive result, can we now infer that these assumptions that we were making actually hold? That's an open question, right? And in addition, so that's like another reason why we might actually really need multimodal evidence to be like, well, if all of these different searches all find the same thing, then maybe that gives us extra reason to believe we found dark matter. And in addition to that, there's still the question of systematics, right? There's still the question of systematic errors. And if given that, you know, the stakes are quite high to claim that you found dark matter, ideally, you would want multiple different ways of finding the same signal or a similar signature to conclude that it's not just like a fluke or something like that you found in the first place, right? And we see this kind of justification in the design report of the LZ collaboration, which is this huge direct detection experiment. And so they write, the 3 experimental tests are direct detection with a proposed LZ experiment, current LHC data, and indirect detection from a proposed indirect detection experiment. Each of the 3 experimental techniques tends to be most sensitive to one region in minimal supersymmetric parameters, parameterized phenomenological minimally supersymmetric model parameter space. This is just like particular WIMP candidate situation. Let's just keep it at that. Although there are regions of overlapping sensitivity, the 3 experimental techniques are subject to very different systematic limitations. A broader goal of dark matter research is to use the 3 complementary approaches to establish the validity of any signal and to identify the properties of the dark matter particle, right? And so they need this sort of like, they explicitly say to themselves that they need sort of the complementarity of all of these different experiments to establish that they found a dark matter particle. So this seems like another potential triumph for robustness reasoning, right? Another in the sense that philosophers of science tend to like it a lot. But yeah, it does seem that in fundamental dark matter searches, we do actually need robustness reasoning. And I think that is, in fact, the case. So now we get to the need for robustness reasoning, which is this second claim. But I still have half an hour. So this is not going to be the whole story. I don't think I'll speak for another half hour, but I do want to flag some other things. Because there has been some concerns about multimodal evidence that has been raised by philosophers of science. And I'm giving you just sort of like one example here. I think, for what it's worth, I think Stegenga potentially overstates, or like sort of, by simplifying things down, he makes the problem very clear, but potentially also overstates it slightly, but it's very useful to sort of bring out the concern. the idea is, the problem that Stegenga raises is about discordant evidence. And the quote here sort of summarizes it. He says, if multiple independent experimental techniques provide greater epistemic support to a hypothesis, it is unclear what support is provided to a hypothesis in the more common situation in which multiple techniques give results that are inconsistent or incongruent. Now, what does he mean by here? By inconsistent and incongruent here? Inconsistent means that your one experimental technique gives X and your other experimental technique gives a result that is not X, right? Those are inconsistent. Incongruent is slightly different. It says, and I mean, fair enough that inconsistent experimental results are a huge problem, right? And this happens in science, and it's something that scientists have to sort of grapple with. Incongruent results are different in kind. That's where one experimental technique says X and the other experimental technique says Y. They're basically sort of like giving results in like different languages almost, like they're sort of or they're constraining different sets of parameters, and so it's not clear how you can actually compare them with one another. There's like questions of how you might even compare the results with each other. And of course, both of these seem prima facie problematic for robustness reasoning, right? Because the whole concept of robustness relies on the fact that you have experimental results that you can compare with one another and that agree with one another, right? And so Stegenga further on in his paper actually argues that the only way around the problem of discordant evidence is choosing which evidence is more relevant than other evidence. And if this is indeed the case, that different, if it turns out, for instance, right, in the case of dark matter, that different kinds of experimental results lead to incongruent evidence, then Stegenga's suggestion is basically choosing whether we prefer the evidence from the LZ experiment or we prefer the evidence from the LHC experiment, right? That's sort of what his suggestion amounts to. But that seems to fly completely against the sentiment that the LZ report was sort of proclaiming earlier, right? So there, again, we sort of have this tension between what philosophers are suggesting and what the scientists are saying. So what's going on here? So is Stegenga's concern actually applicable to the case of dark matter searches? Is it indeed the case that different method-driven experiments lead to incongruent results? And does that actually defeat the purpose of having multiple searches, like multiple types of searches for dark matter? With regards to the first question, I take the answer to be yes. And I'll give you a very short summary of why I take the answer to be yes. But I also refer to Antonis's paper that I mentioned earlier, where he goes in much more detail than anything that I can do so far. So, but sort of a very basic idea, why is it that different types of dark matter searches lead to incongruent results? Well, because it turns out that direct detection experiments and production experiments, or particular kind of production experiments, constrain different sets of parameters. They don't constrain the same parameter space. Direct detection experiments constrain two free parameters. That's the dark matter mass and the interaction cross-section. Model-independent production searches constrain four: the dark matter mass, the coupling strengths at both nodes of your interaction, and the mediator mass. So they seem to be incongruent in Stegenga's sense, right? In the same that these two types of experimental results are constraining different parameter spaces. So it's like X and Y. But does that defeat the purpose of multimodal evidence? Not necessarily. And indeed, I kind of doubt it, because in practice, right, physicists do compare constraints from production experiments and direct detection experiments. If you've seen the sort of plot with exclusions from WIM parameter space, there's like both direct detection experiments and production experiments on there usually, right? And who am I to sort of start telling them that what they're doing is completely impossible? Like that seems, you know, a bit harsh from me. But of course, the fact that physicists do this, right, is in and of itself not sufficient to answer to Stegenga's claim. right? Segenga has raised a serious concern, and there's a need for some kind of response as to why the incongruency of different dark matter searches doesn't defeat the purpose of multimodal evidence. And comparing the production and direct detection searches results is a non-trivial exercise, right? You have to make different assumptions about the target. And as a result from those different assumptions they make in setting up the experiments, they constrain these different parameters. And so in order to make the different results comparable, further assumptions are needed. And again, those assumptions are not always further justified, right? So we do see that like answering to the robustness, like sort of answering to the challenge of incongruent evidence will bring with it, and I'm not going to go through the full details of it, but like will bring with it like further challenges as to how, like what kind of assumptions need to be made in order to make the results from the different searches comparable with one another in the first place. And so they're like, you have to keep that in mind, basically, when you're making these comparisons. But I will say once again that like, although I am optimistic, I have to also recognize that Antonis published a paper recently on robustness in dark matter research, where he goes through an extremely detailed study of different kinds of dark matter searches. And he's sitting right here. Sorry to put you on the spot, and argues again and like sort of raises important challenges to the use of robustness reasoning in dark matter searches that are like open to be responded to, which I won't be able to do here, but I want to flag that that's an excellent paper. So, but let me sort of so I very strongly recommend you go read it. So this brings me sort of to the end of this lecture. It took me less long than I thought. And so let me just briefly sum up what I have done, right? Because we've covered quite a bit of ground. I started out by distinguishing between two dark matter concepts. Fundamental dark matter and astrophysical dark matter is what I called them. I sort of claimed that, I sort of posited that depending on whether an experiment is looking for one or the other, it's gonna put different conditions of success on your experiment. And I argued that in the case of astrophysical dark matter, one crucial condition is that you're gonna have to rely on eliminative reasoning and have to make a case that your eliminative reasoning is successful. I then shifted to fundamental dark matter. And I first went through a sort of a long discussion of how these searches for fundamental dark matter are justified. And based on that, I turned towards robustness reasoning. And I argued that indeed you need robustness reasoning to conclude that any of these searches for fundamental dark matter have indeed found dark matter. But there are some open questions as to how effective you can actually use robustness reasoning in dark matter searches. So that is it. Thank you. And here are some references. Lots of references. There we go. And David Bowie. There's no reason why I have David Bowie. It's just I think it's funny. I made it once for a talk and now I use it all the time. Are there any questions? Yeah.
You said that if the different ways of detecting dark matter gave us different results with one fit together, you think that scientists would just choose the one they prefer? Or that seems to be weird. If they had evidence for a different drug is basically quote unquote true or at least indicated by experiments, then when physicists usually try to make better experiments to determine whether actually two different things may be true at the same time.
Yeah, so this is not my suggestion. I think this is what Stegenga suggests in his paper. Like it's, or at least if I'm correct, right? Maybe I'm misinterpreting it, but that's how I read it, at least that's his suggestion in his paper, that when there are these incongruent results, scientists will have to make a choice. I agree with you that seems, I mean, okay, with inconsistent results, that seems just wrong to me. It seems that when like there's inconsistent results, when they're in direct contradiction with each other, you need to figure out what went wrong there, right? Like we presume that the world is not inconsistent. So like what actually, like that's like an open challenge for investigation. when it comes to incongruent results, it's still a bit strange to me to think that you could choose like using one as being more useful for your purposes than another. Because it seems to me that you'd probably want to like more evidence is better, right? So I think that sort of like based on that ground, you'd probably want to say that you want to be able to incorporate as much evidence as possible. And so if it is incongruent, that you might want to try and make it congruent. I mean, that's what they do, right? In the dark matter searches case. And so, yeah, the like in line with that, I think what the LZ report is sort of pointing at, and I think what sort of generally the sentiment is that like you'd want to try and make things compatible with one another. So yeah, I don't think I agree with his suggestion, but that was his suggestion, at least, as far as I understand it. Yeah. Yeah.
Thank you very much, Siska. And I remember well that the eliminative reasoning is very difficult to frame in Bayesian approach. So in a certain sense, your argument is also an argument favoring material theory reduction proposed by John Norton, because
I've never thought about it that way, but it is in fact, but it's an interesting suggestion, right? So maybe for some background for people who are not as familiar with the literature.
Very beautiful book by Herman. There is a chapter on eliminative discourse, because we don't know which are all the possible hypotheses. So if you eliminate from a Bayesian point of view, there is no real changing modification of probabilities. So it is an argument of the material notion of induction.
Yeah. Sorry, just as background, right? So I mentioned in the first talk that I gave today, Bayesian confirmation as this very dominant view on theory confirmation in contemporary philosophy of science. But what Enzo is pointing at is that, in fact, it's not entirely clear that you can frame eliminative reasoning. You can give a sort of Bayesian reconstruction of it. The alternative that he's proposing is Norton's material theory of induction. And John Norton, who was my PhD supervisor, developed like his own view on inductive inferences. And the idea behind the material theory of induction is that there is no general theory of induction, but rather it is always going to be the background facts that ground any inductive inference and that sort of justify the structure of the inductive inference also that is being used. And so I hadn't thought about it in terms of the material theory of induction, but yeah, I can see how you could make the argument that what I'm doing here is sort of in line with sort of like identifying the background facts that make it that we justify one particular, like that we use one particular kind of inductive inference over another. Yeah, it's a good suggestion. I hadn't thought about it. Thank you. That's interesting. Yeah. Cool.